Hello, my lovelies. How's everybody doing? Are you all enjoying the sunshine? Is it sunny where you are? How are you doing? Gosh, all right. We've already got an exam, a chemistry question in there. Should 1-chloro, 2-iodo, 3-bromobutane be written alphabetically? Technically, you do write the halogens alphabetically, but for A level, you don't really get marks down for that. But yes, technically. Hey, Jalaj, no worries. It's nice to have you back. We'll get started in just a minute, just sort of wait for a few more people to show up. If you're new, welcome. My name is Georgia. The whole idea of these study sessions is kind of that we just run through exam questions. I'll read them out, maybe give you a few tips, give you guys a chance to have a go at them, and then sort of I'll run through the answers and you guys can ask me any questions you like. So we shall get started very soon. Just sort of giving a little bit of time for a few more people to arrive. Do I recommend the year 12s coming to the rate equation webclass? Yes. So for on the platform, today I'm starting to restart the entire year 13 syllabus. So if you want to start learning the year 13 syllabus, then I definitely suggest you come. If you don't want to, if you just feel like it's going to be too much at the moment and you want to wait, then feel free to sort of wait until next year. But yes, I'm starting again, properly starting again. Oh, that's so exciting. I'm glad you're joining soon for Ultimate. I will see you on the platform. Is it too hard? No, Jalaj, I don't think. It's not too hard. You'll be fine. How to revise for the UCAT? Gosh, that's a big thing. A big question. There's lots of ways to revise for it. I think that we would have to have a whole session talking about that. So I don't think I'm going to sort of answer that, but if anybody else has any tips and wants to throw them in the chat, feel free. All right, let's get started then. So just for those of you who are sort of at the NMR ones, the sort of NMR sessions, these are going to be a bit different. So the NMR ones are sort of doing a teaching session, whereas this one's sort of going back to the format where we're just sort of answering questions together. Okay, so this session is on halogenoalkanes, and it's quite sort of varied because the halogenoalkanes reactivity sort of pops into lots of the organics topics, so sort of be prepared. Is this for OCRA? Yes, so very specifically this is for AQA, EdXL, and OCRA, but it's not like a topic that has lots of differences between the other specs. So if you're like CIE or OCRB, don't worry too much in terms of there being things that you don't need to know. But yes, cool. So as usual, at the end, there's going to be a nice coupon code for our website. And as usual, I'll show you around the website and things like that. So wait around for the end for that. Cool. All right, so the first question we have here is a multiple choice as usual. So you got about a minute to have a go at it, and it's reasonably simple. So which of these compounds is a secondary halogenoalkane, A, B, C, or D? So have a go. Have a think about what it might be, and I will let you know what it is in about 60 seconds. Got about 10 seconds until I sort of say what the answer is. I appreciate how confident you are, Jalaj, but I would not bet people 10,000 quid for literally anything. Because Mostly I don't have 10,000 quid to give away, but also I wouldn't want to lose 10,000 if I had it. Are there any slides you can download? Yes, they are in the description. They're in the description for you to download. Cool. All right. So yes, you're right. The answer is C. So really quickly, a halogenoalkane contains a halogen. Somebody said there are no halogens in the rest of them. There are. B has a halogen there. D has a halogen there. A is not a halogen at all, halogenoalkane at all. But C is correct. So it's correct because secondary means that it's sort of in the middle of a chain. So the carbon that it's bonded to is bonded to 2 other carbons and 1 hydrogen, which is exactly the case here. So yes, C is the answer. So well done. So we started nice and simple, sort of ramp it up very, very slightly. So this next question, again, you get a minute for. So this reaction is an example of what? Is it an addition reaction? Is it an elimination reaction? Is it hydrolysis? Is it oxidation? What's going on here? So we're getting a bit more of a mix of answers here. Probably going to give you like another 10 seconds. All right. So those of you who said B were correct. So quite a few of you said A. So I just want to remind us of the difference between an elimination and an addition reaction. So an elimination reaction is when you're breaking single bonds to create double bonds, and an addition reaction is when you break a double bond to create single bonds. So the backward reaction for this is an addition reaction, because we can tell here that we've got an alkene, we've got ethane here. So the backward reaction is an addition reaction because you're adding single bonds and getting rid of a double bond, but the forward reaction is an elimination reaction because you're going from something with single bonds and then making double bonds. So I hope that makes sense. Does anyone have any questions on that one? Isn't this nucleophilic addition? So the backward reaction is addition, but this is an elimination reaction. This is a year 1 topic, and it's in either, depending on your spec, it's either in the halogenoalkane section or in the alcohol section. Most specs don't require the mechanism. No? We're good? All right, then I am going to move forwards. But the OH is a nucleophile. So a hydroxide group, it can act as a nucleophile, and it does act as a nucleophile in this case, but it's the question of what it's attacking, right? So keep in mind, the only people that actually need to know the mechanism are AQA. But if you sort of think about, so what if we remember that a nucleophile is an electron pair donor. In this case, the electron pair is donated to a hydrogen, which then donates its pair of electrons into the double bond to form the double bond. And then the bromine is sort of kicked out. So it is a nucleophile, but that doesn't mean that it's a substitution reaction. I hope that is helping. You like the mechanism, so it's fine. Yeah, but you don't need to know the mechanism unless you're AQA, in which case you do need to know the mechanism. Yeah, sorry, AQA. But yes. All right. So it attacks the CBr. No, it attacks a hydrogen. You do OCRA and your teacher says you need to know it. So okay, so I can always be wrong, obviously, because human. But I was like literally making a web class on alcohols today. And so I checked the spec for elimination reaction mechanisms for OCRA specifically, because that's one of the boards that I make the classes for, and it said no. But of course, I am fallible as a human, so I maybe United One double check the specification, but I do remember the specification saying mechanism not required. Why is it not nucleophilic substitution? Remember what substitution mean, guys. Substitution reactions are when you replace one functional group with another functional group. That's not happened here. If you're asking why nucleophilic substitution hasn't taken place, that's a whole other question. So it sort of depends on the conditions. And in this case was sort of that the conditions are not part of the question, and you can tell that they've sort of helped you out by not putting substitution in there, because obviously that could happen with the reagents. But yes, but I'm going to move forwards, because otherwise we're sort of going to spend ages doing this. This next question is like an interesting one, because it's a little bit sort of more applied. So I'll see what you guys make of it. So the reaction of butane 1,4-diol with butane dioic acid produces the polymer PBS used in biodegradable packaging and disposable cutlery. Butane dioic acid is produced by two different processes. So we could have process 1, where we use aqueous sodium hydroxide reacting with 1,4-dibromobutane to make butane 1,4-diol. And then butane 1,4-diol is oxidized to butane dioic acid. So that's the first process we could use. Or we have process 2, where glucose reacts with carbon dioxide in the presence of microorganisms to produce butane dioic acid directly. And the carbon dioxide used in the process is obtained from a local factory that produces bioethanol. So the first part of this question, and the only part of this question that we're going to answer, says deduce one safety reason and one environmental reason why process 2 is preferred to process 1. So why people? Why do we prefer? So we want one safety reason and one environmental reason that we like process 2 better than process 1. And it's 2 marks, so you need to say 2 things, but I'll run through all of the possible answers. You've got 2 minutes, go for it. So please, when you're writing it in the chat, state whether you're writing your safety reason or your environmental reason, because part of answering this question is being able to tell the difference between the two. It is cool, Kang. So that sort of stuff is usually like there's a whole field at the moment called synthetic biology, where you use microorganisms to do a lot of chemistry stuff, which I think is like pretty cool. It's a specialism I really love. So why do we prefer process 2 to process 1? Got about another minute. I've seen a few answers in there, but like I've seen mostly environmental answers. So if some of you could shove in some safety answers, that would be very useful. So remember, you need one safety, one environmental. Okay, fair enough. I really like when students feel comfortable to say not sure. I think that is fabulous. I think we've got some people drawing a blank on safety. I might give you a bit of a clue. Have a look at the reagents in process 1 and tell me what safety sort of problems we might have with them. So that's your clue. Safety of the product is flammable. Okay, I'm going to get started, and then I'm going to sort of tell you what the options were, and then I'm going to run through some of the things you said, and sort of like we'll talk about them as well. So I'm going to start with the safety reasons, because that's what it says first. So for safety wise, all we really wanted to do is like literally run through so like the way you kind of address these kinds of questions is you want to be using the context heavily. So I'm literally just going to go through the context and pick out things that are safety implications of each step of process one. So process one, first of all, we can see it uses sodium hydroxide, and sodium hydroxide is the first thing we can consider. Sodium hydroxide is a strong base. And strong bases are corrosive, they're caustic, so there's a safety implication in that. So that's the first thing we can say. So that would have gotten you 1 mark if you said sodium hydroxide is corrosive or caustic. So that's just from me, like looking at my process, picking out the first reagent that's in there and sort of talking about it. The second reagent that I could talk about, the next thing it says in process one, is the 1,4-dibromobutane. So then we want to be thinking about bromine compounds, and I did see some of you guys putting this in. So bromine compounds are toxic or poisonous. You can say either. Toxic or poisonous, either would be fine. What does caustic mean? Caustic is sort of like another word for corrosive. So it's just like you could use either word. I saw some other bits in there. So I got some of the things, some people saying flammable. Flammable is not really correct. So flammable doesn't really work in there. Heating under reflux. Heating something up, I see why you might say that, but you could heat something up without using a flame. So then that's not particularly dangerous. Then that's just about as dangerous as cooking pasta, right? On an electric hob. So you can't really sort of argue for having to do it under reflux being dangerous, but I see why you might think that. You need to use reflux in process one? Probably. Free radical substitution of the bromo compound. No, that's not radical substitution. How did I know the second point? The bromine compounds were toxic. I just remembered that bromine compounds were toxic. So that should come under when you sort of study your halogens in general. I mean, like you can kind of assume that most of the halogens are not sort of fit for consumption. What word is written after corrosive? Caustic. Caustic basically just means corrosive. So it's just like optional words. Cool. So those are my kind of safety issues. I can't really talk about, so somebody said stuff about the butanedioic acid, the product being flammable. So you can't talk about the product being a safety concern for process one because the product is in both process 1 and 2. So if you're making butanedioic acid in both, then you can't really pick one over the other because of the safety concern. They both produce the same thing. So you can't really say that. Okay, so those are my safety risks. You guys were a lot better at picking out the environmental risks. And I wonder if that's just because environmental stuff is kind of in the news. So it's worked into your daily life in general, so which is good. It's good, always good when science has worked into daily life. But we've got some possible, so those of you saying that like the reactants are flammable then, so they're not any more flammable than the reactants for process 2, right? So you can't, if we sort of process 2 produces bioethanol, or uses stuff that's used from producing bioethanol is just as flammable, and butane 1,4-diol can be flammable. So if both processes involve flammable compounds, then you can't say that you're picking one over the other for something being flammable. But yes, continuing. So we've got some, lots of you said things about, so actually I'm going to scroll up. Yeah, so United One said bioethanol is sustainable. So you kind of, when you want to talk about sustainability for process 2, I'm going to start with glucose, right? Because if glucose is our feedstock, we can definitely get glucose from plants. So I'm going to sort of talk about the glucose more than I'm going to talk about the bioethanol, because the bioethanol is kind of like the process for which you get the carbon dioxide, whereas glucose is kind of directly involved in process 2. So if I was going to pick one to talk about, it would definitely be the thing more involved in the process. So glucose is a renewable resource, because of course we can grow it. So that's one option. So we've talked about glucose there. And we also know that we're reacting it with carbon dioxide. What do we call something that sort of takes in carbon dioxide, sort of environmentally? What do we call that? When you sort of find somewhere to put the excess carbon dioxide, does anyone remember? Carbon sink, yes, yeah, that's what I was going for. So you could also say that process 2 is a carbon sink, or you could say it's carbon capture. Carbon hoarder. It's not the correct term, but I like it. Somebody said something up there. What are the conditions for alcohol to carboxylic acid? That's you want to do that under reflux. And you need, of course, you need your reagent. Cool. Did somebody else say something? Can't remember. If they did, say it again. But we've been through our glucose. We've talked about using carbon dioxide. And we could also talk about the fact that carbon dioxide that's used in the process is obtained from a local factory, right? So then we can talk about the fact that it's recycling CO2 from the local factory, which is also really cool. So process 2, can you say that alkalis are an irritant? I wouldn't really, that's something you would take into account in a risk assessment. But if you're thinking about the overall safety implications of like an industrial process, something being an irritant is just not sort of important enough to count. So I wouldn't sort of use irritant, because if something's corrosive and it's an irritant, then the corrosive thing is definitely the more important thing. Does that make sense? So carbon sink is as good as it's taking carbon dioxide in. Yeah, exactly. Yeah, so we're like finding somewhere to put the carbon dioxide. You don't understand the carbon sink one. So a carbon sink is just essentially like a method that we use to take carbon dioxide out of the air and put it somewhere so that we aren't sort of contributing to global warming. So other carbon sinks include, like, we sometimes like shove carbon dioxide under layers of sediment in the ocean, or like, for example, just limestone cliffs, like the calcium carbonate in limestone cliffs, that counts as a carbon sink. So it's just somewhere we put carbon that's not in the atmosphere as carbon dioxide. So this technically is a carbon sink. This process is a carbon sink because we're taking carbon dioxide and we're making butanedionic acid with it. Could you say it's carbon neutral? I think that you probably would get the marks for saying it's carbon neutral, but I would say that you don't know that it's definitely carbon neutral, like the whole process. What you could say was carbon neutral is the bioethanol. So you could say that the carbon dioxide is gained from a carbon neutral process. But like the production of bioethanol is carbon neutral, right? Because you're growing plants which take in carbon dioxide and then using bioethanol. So anything you release from the bioethanol is going to sort of be balanced by the growing of the plants. But then if you then use that carbon dioxide in making butadienic acid, it's kind of like, it's better than carbon neutral. It's taking in the excess carbon dioxide. So I would kind of avoid saying carbon neutral unless you're sure that it's definitely carbon neutral. Yeah, so you could probably say the production of the bioethanol itself is a carbon neutral process, but I don't think you could just sort of very well argue that the whole process too is a carbon neutral process. Yeah, and Pablo says it's not really carbon neutral as there's transport of the product to account for. Yeah, so, and there's also lots of little bits like that. Somebody else said, would fizzy drinks be a carbon sink? I mean, like technically while they're in the bottle, I suppose you could argue that, Amelia. So yes, if you want to drink some Coca-Cola and sort of argue to yourself, well, it's a carbon sink. I mean, like, I really feel like the drink is more of a carbon sink because it has a bunch of glucose in it. So that's also something to think about. Somebody else asked me a question, but I can't find it, so I'm going to leave it here. Why can't you talk about bioethanol? You can talk about the bioethanol. It's just that if you want to talk about there being a renewable resource, it makes more sense to be talking about the actual feedstock of the reaction rather than where the carbon dioxide is coming from, if that makes any sense. More likely to get marks. But yes, next question time. Let's move on. All right, so this one's nice and short, but it's part of a long question. So the first part of this question says, allyl bromide is reacted as shown below. So we've got allyl bromide. So allyl just means like a propene-y bit. So you've got propene, and then you make one bromopropane after step 1, and then you've got step 2 where you're reacting with Cl2, and you get a mixture of organic products after your step 2. So the first part of this question says, state the reagents and conditions for step 1. For step 1, and I want you guys to be really careful about this one. I want you to be really, really careful. I'm going to just tell you that the thing that you're assuming it is probably wrong. So just sort of read it really carefully again in your head, and I'll give you about a minute. Yeah, so I can see sort of us improving our answers. So I know that lots of you sort of assumed at the beginning, oh, I'm making a 1-bromopropane from an alkene, I must be using HBr, not sort of realizing that we already have the bromine in there. So all we're doing is reducing the double bond. We're going from an alkene to an alkane. That's the reaction that's taking place in step 1. And those of you who were saying hydrogen and a nickel catalyst, that's perfect. So we want hydrogen and a nickel catalyst. How do you know that it's a nickel catalyst? You just have to memorize that you use, because all we're doing is adding hydrogen across a double bond. The sort of, the thing that you use for that is hydrogen, and then to catalyze the reaction, nickel. Do you have to say heat? Nope. No, you don't necessarily need heat. Should you write catalyst in your answer? Yes. So you must always make the distinction between when something's a reagent or when something is a catalyst, because the catalyst is not getting used up, right? And because the question specifically said reagents and conditions, if you just put hydrogen and nickel in there, then it looks like the nickel is a reagent. You want to make it clear that it's one of the conditions, which is a catalyst. Are there any other catalysts? Not in the specs, but you could totally use palladium. But I wouldn't write that in your exam, because in the spec it like says nickel. So just say nickel, but you could use palladium. You could use like a palladium carbon catalyst, but we don't need to know that. What are the conditions for halogenation? X2 and... You know, I don't know off the top of my head. I can't remember. Somebody Google it. Although I suspect that you don't need a condition. You don't need any conditions for that reaction, I suspect. What about lithium tetrahydride? So you can use LiAlH4 for some of these reactions, but you have to make sure there's not going to be any interaction with the bromine. So it's a lot safer to use something like hydrogen in this case. How are you supposed to know that? How are you supposed to know what? This. You have to remember it. So you need to know, you need to look at the reaction and say, okay, the only thing that's changing here is my double bond. I'm going from an alkene to an alkane. That must mean that I need to reduce it. And the reduction reagent that I use is hydrogen with a nickel catalyst. What's the name for step 1? Hydrogenation, which is a type of reduction. Can you use other catalysts? As I said, technically, chemistry-wise, you could also use a palladium catalyst, but it's not on the spec, so don't write that. All right, moving forwards. So the second part of this question is about step 2. So I'm going to flick back to step 2 in just a second, but it says in step 2, 1-bromopropane reacts with chlorine by radical substitution. So this is quite a long one. It's a 5 marker. So what we're doing is outlining the mechanism for the monochlorination, so single chlorination, that's all that mono means, of 1-bromopropane. In your mechanism, you can show the formula of 1-bromopropane as C3H7Br. That makes things faster. Include the names of the 3 stages in this mechanism, state the essential conditions, and all the termination steps. So when it sort of says all the termination steps, that's kind of suggesting, look, you don't need to write every single propagation step. There is, because a lot of them sort of just make themselves again. So just the major ones will do. And I just gave you one of the part of the answers, but I'm gonna let you guys just sort of like start having a go. I'll give you a few minutes, and then I'll go over it. That's a lot to write in a comment. Yes, it is, Pablo. You're right. Should the arrow be reversible? No, this is not. You don't need to write this as a reversible reaction. You're welcome, Pablo. It's lovely to have you. All right. Okay, I'm going to get started. And when we get to the termination steps, I might ask you to sort of tell me the termination steps when we get there, because I can see all of you guys remember that this is radical substitution. So we have an initiation, a propagation, and a termination. And it said include all the names. So please read the question and include everything it tells you to. So the first thing we're going to do is our initiation steps, which all of you have sort of gotten. Apart from you guys, a lot of you didn't put in the conditions. You have to put in the conditions because it asked for them. It said state the essential conditions. So please, like when you're sort of doing your exam, if you're the kind of person that misses bits of information out of long contexts, either make notes, so write little notes for yourself about the things it told you to include, or like highlight the things it told you to include so you don't forget them. So it told you conditions, and that's in the, yeah, exactly, UV light. That's in the initiation step. So you can just put UV at the top of the arrow, or you could have said UV light required, but then we'll get 2 chlorine radicals. So most of you got that bit, the Cl2 making 2 chlorine radicals. So well done, everybody that got there. And the next thing we've got are our propagation steps. And there's only really 2 that we need to mention. So we know that we're reacting 1-bromopropane, and we know that we can just write it as C3H7Br, which is just so nice because it's really long to write it in the full way. So we've got C3H7Br, and we know we're first going to be reacting with the chlorine radical because it's the only one we've got there. So if we react C3H7Br with the chlorine radical, then the most likely radical reaction is that one of the hydrogens gets plucked off, and we're left with a carbon radical. So we're going to have a carbon radical there, and then some HCl. So that's our first propagation reaction. So the second propagation reaction must, of course, involve the radical that we just made. So we made this carbon radical. Oop, that should be a 6. Sorry, that should be C3H6, because of course we've just sort of attacked one of the hydrogens on there. So we should have C3H6Br. Yes, I did. I did forget to remove the hydrogen. Cool. And then the next reagent we're going to put in there, we could put in the C3H7Br again, but then we would end up with the same, a very similar product. So as we don't need to put all of the possible propagation reactions, I'm just going to do a main one. So I'm going to put in Cl2, which should give us chlorobromopropane. That is a mouthful. And another chlorine radical. So that's the only that is the only 2 propagation reactions I'm going to bother writing. And the last thing is, of course, I can't use my words today. The last thing, of course, is our termination reactions. So it said we have to write all of the termination reactions. So how many should I have and what are they? So I'm not sure, not many of you sort of gave me termination reactions. I didn't give you enough time, so go ahead and do that now. So how many termination reactions? Yes, you can write it like that, Kang. Yeah. Yeah, we should have 3. Thank you, VBO3. We should certainly have 3. So I'm going to need to see 3 in the chat. I don't know how they put the dot there, but you could just copy and paste their dot. How much of this is year 13? This is all year 12. None of this is, yeah, this is all year 12. Okay, cool. Yeah, so most of you got that the 2 chlorines could come together as Cl2, of course. We're just reforming the Cl2 from the first place. And then I can see that somebody's VBO3 is saying that we could combine 2 of the thingies, brain, 2 of the bromo sort of propane radicals to make a dibromobutane. So that's what I'm going to do. I'm going to have 2 of those. I won't put the times in because that's not very chemistry, is it? So I should have C6H12Br2. And then last but not least, we need our chlorine radical joining with our bromopropane radical. So that's the last possible combination, giving us a chlorobromopropane. Cool. So that's all of our 5 marks. So well done, everyone. It's a long question, but it's one of those that if you sort of just remember how radical reactions are, it's reasonably simple to get the marks. It's more memorizing. It's not like you're going to have to apply it. There's no bullet point on your keyboard. There's none on mine either. I don't know. I don't know. If somebody could say how you're getting your dots, that would be perfect. All right, what time is it? I got a bit of time. Let's do this. Let's do one more. Is that the last one? Oh my God, I'm so on time. I'm so proud of myself. And you. It's not all about me. Okay, last question. So this last one says radical substitution produces a mixture of organic products. Suggest 2 reasons why. So we want 2 reasons. Why do we get a mix of organic products? And you got a couple minutes. No worries, Jalad. You do what's best for you. So we've sort of got a lot of sort of like one of the options, but not a lot of the other option. And I thought that the other option was the more obvious one, given the previous part of the question. Think about the previous part of the question. What was it about that gave us a mixture of things? So lots of you are sort of lots of you are doing very well at sort of explaining why you might get sort of random collisions happening. And I think that's really important, but it's sort of more of like an explanation of the explanation, if that makes any sense. Freya's got it. So the first one, or the second one of them is that there's more than one termination product. So we literally just had a look at that one. There's more than one termination product. So we on the previous page, we saw how many different products there were. So there's more than one termination product is the first option, or at least in my head is the first option. And the second option is the one that lots of you were saying, that substitution can take place sort of anywhere on the chain. So well done, those who got it. You don't get the first point. So that's literally, the first point is literally just sort of saying out loud the last step of any radical substitution, where the radicals can come together in the termination step in lots of different ways. So that's the first reason that radical substitution produces a mixture of organic products, just because the termination, there's more than one termination step. There's more than one termination product. So that's the first one. And then just like what else, the other things that you guys were saying. Are there no marks for talking about further substitutions? I would say yes. So given that this sort of question is kind of talking about a mono substitution, then I would sort of avoid it. But as it's not that part of the question, then I think you would get away with saying multiple substitutions. Yeah. Oh, that's very sweet, Heather. What is further substitution? So like you could have multiple chlorines substitute rather than just one. Wait, you mean the whole mechanism chain? I don't know what you mean by that, crazy wolf. And that is, yeah, adding more chlorines. All right, I feel some of you are confused. Have you guys, like when the product keeps reacting with radicals, as in the termination, not when the product keeps reacting with radicals, when the radicals keep terminating. So remember, termination is when two radicals come together to make a normal sort of stable molecule. And there's 3 termination steps in this one. Either 2 chlorine radicals could come together and make Cl2, that's one product. Or you could have 2 of the bromopropane radicals come together to make brain blank, hexane, dibromohexane, or you could have the chlorine radical react with the bromopropane to make chlorobromopropane. Those are 3 products. That's a mix of organic products just from the termination step. And that's from just the same substitution. So that's what we mean by the termination. Can take place anywhere on the chain. So substitution, so like if we think about, we didn't draw this, but let's say this is our bromopropane, and I'm not going to draw all of the hydrogens because I need space. I could either have substituted my chlorine there on the same carbon as the bromine, or it could have been in the middle, or it could have been at the end. So those are technically different products. Like it removed the spider webs. Ah, that's good. I'm really glad. Yes, they're on Tuesdays and Thursdays at 3 o'clock. Cool. I'm going to finish here, guys, and do the whole like usual thing where I tell you all about our website. So if you know that already and you've seen the website and you've heard me ramble about it before, feel free to, you know, like go and drink some tea or whatever people do. What's the process called that we just did? That's radical substitution. That's radical substitution. But if you haven't seen the website and you'd like to know sort of like more about like what I do and what sort of this whole thing does, Snap provides our like whole YouTube channel. We actually have our own platform. 24 hours is the code length. So we have like a whole platform where we've created lots of things like this home study club to try and get you guys through your A-levels. So the YouTube stuff is always free, but the platform is paid for because you get lots and lots of stuff, and I'm going to show you the stuff that you get. If I can make my computer do what I want it to. I'm making it do things. It hates me. As soon as I'm on live stream, my computer decides to malfunction. I think it's just sort of like a Sod's Law-ish type thing. Drink carbon sink fizzy drinks rhymes, so it must be true. I like that. Yes, everything that rhymes must be true. See you later, Jalaj. Thank you for recommending us. But yes, so this is our website if you haven't seen it before. And essentially you would sign up and then like subscribe to one of the your specification and your subject. So if it's AQA chemistry that you're doing, this is what it would look like. So you have like all of the topics from AQA chemistry, and then you would click on one that you want to like have a look at, and then we would sort of get you to do a diagnostics quiz so that you sort of we see where you are, and then by your answers from the diagnostic quiz, which I'm not going to do because that is just going to take too long. We have like a bunch of videos that will help you sort of understand the stuff, and you can like skip ahead to sections if you sort of get one section but not another. So that's sort of like the basic-y stuff. And then you would do another quiz to see how you are. And then you'd be able to tell if you actually sort of like took the stuff in or whether you need to sort of think about it a little bit more. And then even after you've done the quiz, we have exam questions. So we've got sort of exam question run-throughs in the video where we sort of tell you where you would get your mark for specific exam questions and things like that. So that's sort of in our basic package. And then if you subscribe to the pro package, you get these exam packs where essentially we spent ages making a bunch of like exam questions. So like people tend to run out of exam questions, especially as the all of the specs sort of renewed in 2015. So when you run out of exam questions, you can use our questions, which we've made like as similar as we possibly can to each specifications exam, and then you can mark them yourselves with solutions and sort of like mark yourself right or wrong and track your progress and things like that. The next chemistry class on YouTube is on, what day is it today? It's Thursday, so it's on Tuesday at 3. And then if you want me around me, then you can subscribe to the ultimate package. So where there's web classes, like in 12 minutes, I'm going to be sort of restarting all of the year 13 stuff again. So we're doing the rate equation. And that's sort of like running through the whole syllabus again. And pretty soon we're going to be running through the whole year 12 syllabus again, because we've almost finished it. So we're doing the alcohols class on Tuesday, and then we'll be starting again. So this is a great time to subscribe because you'll get to run through all of the syllabuses from the beginning. My colleague's going to drop in the pricing thing in the chat, hopefully. And then I won't have to go to that page. So we've got loads of different exam thingies. Brain, say words that make sense, please. Lots of different web classes. So we've got a book club, and then we're doing like a careers in chemistry thing on Monday, and we're going through our practical techniques and all sorts of bits and bobs. And then this moose is completely unrelated to rate equations, but I've run out of chemistry icons, so it's a moose. And then we have our drop-in sessions. So the last thing, the drop-in sessions, where you can come in and just ask me questions or ask me to go over topics that you are confused about. stuff like that. So that's it. That is our platform. I know I'm always banging on about it, but that's sort of like what we do, and it's important for me to show you what we do outside of YouTube, of course. So what was I going to do? Oh, I remembered. I was going to show you the code. The code. Ooh, the person living next to me is banging with a hammer. I hope you can't hear that. Yes, set reminders on YouTube for all of our Majigs live sessions. And then here is your £10 off your first month for whatever package you subscribe to. We've got like a bunch of different price points. So like hopefully like one of them is affordable. And if none of them are affordable, then I'm still here on YouTube to help you guys out. So that's sort of like the best we can do. Obviously, it's important to have that kind of range. So you pay per package, per subject. Yes, but if you do lots of subjects, then you get a discount. If you want to know what the discount is, I can't remember. So just drop us an email at hello@snapprovise.co.uk and then someone will tell you what the discount is. But yes, if you do multiple packages, you do get a discount. But yes, I'm going to finish off there because I need to prep for my next class, and also the banging is next door is getting on my nerves. So I'm going to do that. Last question, is it easy to cancel the subscription after a month or so? Yes, you're not like locked into a year or anything. Yeah, you can cancel at any point. So that's fine. So like if you like started and you didn't like it, you could just cancel, and then you would have only paid for the first month, and then that would be fine. Is the first month is the first month a free trial? No, not currently. We are sort of talking about whether we should try and do a free trial. So we're thinking about that, but at the moment it's not a free trial, but you can get a discount with this nice code. But yes, I wouldn't sort of like, don't hold me to the definitely there being a free trial thing. It's just sort of in discussion. But yes, I'm going to head off now. Have a lovely afternoon. Thank you for sticking and staying, and you guys are wonderful students. Yes, thank you. I will see you guys, I don't know, Tuesday. Yes, because I know what day it is.